Okay, so what did we do last time? Last time we considered the last thing we did was considering the dimension theorem. We have also proved it, right? Well, I have first to make it work here. All right. So last time we considered the dimension theorem for linear maps, and we proved it. And what we will do next? Well, I think we're almost finished with the basics of linear maps. That is like the most basic things around about them. And then there will be some specific things, and I don't know which of them I would like to teach you. We'll see about that. Maybe I'm also mistaken that we are almost done with the general things. Well, let's see. Let's see how it goes, and we'll adjust our endeavors accordingly. Right, so last time we had the dimension formula. I hope you recall it. It is just if we have a linear map from space V, finite dimensional vector space, to a space W for which nothing is specified except for that being a k vector space just like V. Then we have the following formula that this finite dimension V is just the sum of the dimension of the kernel of L plus the dimension, of course, dimension, right? Dimension of the kernel of M of L plus the dimension of the image of L, right? That we have proved. And now we'd like to look at some corollaries. Corollary of the dimension formula. Let L from V to W be a linear map, and let the dimensions of V and W be both finite and even equal. Let dimension V equal dimension W equal some n in the natural numbers, right? Then have that the following are equivalent, that the following are equivalent. All right, first is that L is just an isomorphism. L is isomorphism. By the way, we should prove a lemma that what was that? If there is if the vector space is isomorphic, then also the dimensions are equal. That is to wrap up the result that isomorphic actually means that we can really completely identify the vector spaces, but that is very easy if V and W are isomorphic. Finite dimensional vector spaces. Finite dimensional vector spaces. in dimension V is equal dimension W, right? Just for isomorphic vector spaces, their dimensions are equal, and that is very easy. You just take a basis of V, and then you immediately know that we have that those vectors are linearly independent in W because L is an injective. If L is our isomorphism, then it is an injective linear map, right? Because L is then bijective if it is this isomorphism, right? Injective linear map means that those vectors U1, n are mapped by our isomorphism to L of U1, LVN. They are linearly independent, and then if you had the possibility to add another vector W, then you just know that the pre-images are then linearly independent, and then we would have more linearly independent vectors in L minus 1, L minus 1 of that, where this, because of bijectivity of L, is just identity map, right? And that V1 to Vn L minus 1 of W, that would be a basis of V, which would have a number of elements in V. Okay, oh, let me do it properly. Let me do it properly after we finish this theorem, maybe, or maybe we'll need it, or we'll see. That's very easy, but I don't want to do it just in that sloppy way. I want to really understand how it works, so let's leave that for now. All right, L is isomorphism. All right, should be 1, right? No, that should be 2, I guess. Right, that should be 2. All right, L is isomorphism is equivalent to, oh, maybe 3. Okay, L with isomorphism is equivalent to dimension of kernel of L is equal, well, to 0, 3, image, dimension of image of L is equal, of course, n. So if we have that the dimension of V is equal to dimension to W, then being isomorphism is equivalent to having a kernel equal to 0, which means exactly having dimension 0, and is also equivalent to surjectivity. And the proof is very simple. We can just go for it, right? If L is isomorphism, then of course that follows, right? Because it is bijective and injective, and if it is injective, then the kernel is the 0 vector, and then the dimension is 0, right? Then from here to here, well, dimension of the kernel is 0. Use the dimension formula. Using the dimension formula, obtain that this is 0, and then dimension of V is exactly dimension of image of L, which means that image of L was subspace of W anyway, right? And now the dimensions are equal. So you could just, since linear independence is given, use the replacement of all vectors in the basis, and you would just see that the basis of dimension, that the basis of the image already is a basis of W, and with that the equality follows, right? You could use the replacement that we have also used last time. We could replace the vectors in the basis of W just one by the vectors in the basis of the image, right? And so you would have that this basis of the image gives a basis of W, and with that, of course, both spaces are equal because the above spans of this basis of the image, right? So this is also clear. And back there, well, if this is dimension equal n, then we use same argument here, right? We use same argument and obtain that image L is actually equal to image L W. I mean, the same argument that we used here, where we got this just from dimension 4, right? Okay. I was already there, right? Okay, let's start again. We have isomorphism, then by injectivity, we just have that the kernel is only the zero vector. Then, of course, the dimension of the vector space that contains only the zero vector 0. Then we just use the dimension formula to establish that dimension of the image is n, because if we plug in here the dimension formula, we get the dimension of the image is n, and then this argumentation gives us from dimension equal to n already the surjectivity, because if dimension is equal to n, then we have anyway, that it is a subspace of W. This is just that it is a subset was the definition of the image. It was vectors in W who were images of some vectors in V. So the image is by definition a subset of W, and that it was a vector space we have shown. So it is a subspace. Now it is a subspace and it has a basis, and this basis is has an elements exactly like the dimension of W is this n, and we could then take a basis of W and we could replace all elements in that basis successively by elements of the basis of the image, as we have seen, and with that we would have that the basis of the image gives us a basis of the space W, which means that the span of that basis of the image is W, and of course, just by definition, the span of the basis of the image is also image L. So we have surjectivity, image L is equal to W, right? And injectivity, well, injectivity, just use the dimension formula, and you get that here you have n, here you have n, and then you have n minus n. Dimension of kernel is equal to 0, and so only the zero vector is in it, because if there would be more than zero vector, then we would have, of course, at least dimension 1, because any vector other than zero vector is linearly independent with itself, and so dimension should be at least 1. Right, because by dimension 0, we couldn't just represent this vector linearly. Right, this finishes the proof. clearly we have proven the equivalence because that follows that, that follows that, that follows that. And if you now take any statement of those, you start at any statement and you get to any statement, and we are already round 2. So the equivalence of the three statements is proven. Right. And now about that, well, that was an attempt on lemma. Let V and W be isomorphic k-vector spaces which is written as V isomorphic W. Right. Then dimension of V isomorphic finite dimensional, but of course you can just by contraposition not by contraposition, if you have an infinite vector space, then you can just apply same argument which we will apply now to show that the dimensions both can't be finite, right? But let's look at the argument. Finite dimensional k vector spaces, right? In dimension V is equal to dimension of W, right? And the proof is, well, you recall isomorphic means there is an isomorphism. Proof let phi from V to W be an isomorphism then let BV equal V1 to Vn, so it is finite dimensional, so the basis will have a finite number, right? Let be that the basis of V and call this finite number n, right? Okay, then we know from injectivity of L that L of V1 to L of Vn are linearly independent in W. Right, we had that if the linear map is injective and goes from a vector space into another vector space, and we just take linear independent vectors, then V will be mapped to linearly independent vectors as well. Right. All right. Now assume L of V1, L of Vn is no basis of W. Then, since the vectors are linearly independent, there could be only a problem with the span. So the span is not the whole vector space, right? Definition of the basis, linear independence is satisfied, so could be only a problem with the span. Then span of L of V1 to L of Vn is not equal to W. Of course, it is a subspace. Just by definition of a space, it is all linear combinations of these elements in W. So it is, of course, a subset of W. So that means then that the other subset relation is not satisfied. Then there exists W and W with W L of V1 L of Vn are linearly independent. This is just the formulation of the linear independence that we had, right? The linear independence meant L of Vi lambda I what I mean lambda I L of Vi plus W some lambda is equal 0. So and we take exactly this W for which that is not true, right? And then if that would not be in the span, then the vectors would be linearly independent, because if the vectors are not linearly independent, this is contraposition, right? If the vectors are not linearly independent, and we show that the vector is not in the span, and that means if the vector is in the span, then the vectors are linearly independent, right? So that is linearly dependent, right? So sum of those lambda or lambda 1 until lambda n, sum of those scalars is now not equal to 0, right? Then lambda is certainly not equal to 0, because if lambda would be not equal to 0, I will assume we are assuming linear dependence and assume not all of lambda 1, lambda n, lambda k are equal to 0. So, assuming that they are not all equal to 0, and we'll look that they give a linear combination nonetheless, so that this linear combination gives 0. And from that, if we assume that and we assume that, then lambda can't be equal 0, because if lambda would be equal 0, then of course this would be 0 and this would be 0, and by linear independence of these vectors, which is already established, all lambda i's would be 0, and then every coefficient would be 0, but we wanted to assume that it is not the case. So if we assume that it is not the case, this lambda can't be 0 among cover, and that gives W is equal minus lambda I lambda I, which shows that W is in fact in the span of those vectors, right? That's by definition of the span. And so we have proved the contraposition. If the vectors are linearly dependent indeed, then W is in the span of those vectors, right? And having shown the contraposition, we have this. That means if we just take the contraposition of the contraposition, because the contraposition we have shown, we take the contraposition of the contraposition, then this reads exactly if we span, if there exists a W in W, sorry, I have to be a little slower. So here we have proved the following. We have assumed that the vectors of Vi and W taken all together, they are not linearly independent, right? And from that, we have concluded that W would be already in this span. The contraposition of that, of what we have shown here, would be if W is not in this span, then those vectors are not linearly dependent, because here we have assumed that they were linearly dependent, right? And here we assume it is not in the span, and then those vectors would be linearly independent, right? And this is what happens here. We say that the span is not equal to W, and then there exists, so the span not equal to W means exactly there exists W element W not in the span, and W element W not in the span would mean that this W with those vectors is not linearly dependent, and that means they are linearly independent, right? Okay. Right, and then L of minus W, L of L minus 1 of W, L minus 1 of those vectors, which gives exactly that, right? Just applied L minus 1 here, 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 and here. Then we know that those vectors are linearly independent in the space V, right? That we just know because L is a linear map, and so V.III images or any things taken in V.III images would be just linearly independent if we took them of linearly independent vectors, but now those vectors are linearly independent, and those are certainly the vectors in corresponding pre-images, so they are linearly independent in V, which contradicts the assumed dimension V equal n. And that we assumed just here, where we have assumed that V1 to Vn would count the basis elements of a basis BV of V. So the dimension was n, and here we have n plus 1 vectors, and they are supposed to be linearly independent, which of course is a contradiction to dimension V equal to n, because again we could just replace we don't even have to replace. We have exactly the spaces V1 to Vn, right? And now we have an additional vector, and we know this is a contradiction to linear independence of those vectors, because those vectors actually span in this vector by the property of them being a basis, right? Then this shows okay, if we got a contradiction, then our assumption was wrong. And what assumption was that? Oh, that it is no basis. So it is a basis, and this basis has n elements as wished, and then the number of elements in this basis, that is the dimension of W, is equal to number of elements in this basis, that is the dimension of V, and then the dimensions are equal. This shows that L of V1 up to L of Vn is indeed a basis of W, and with that we have, of course, n let's do it like that. Dimension of V is equal to the number of elements in a basis of V is now just equal to the number, right? This is the number of elements in a set is equal to the number of elements in the set L of V1, L of Vn, which is equal, since we have established that it is a basis, to dimension of W. Right, and let me maybe recall what we did, because it was a little confusing how I presented it, because I wanted to explain it properly. So we assume that the vector spaces are isomorphic finite K vector spaces, right? Isomorphic and finite, that is finite dimensional K vector spaces. Finite dimensional, exactly. Then we wanted to show that under this condition, the dimension of V is already equal to dimension of W. For that, it suffices to just give two bases, one of V, one of W, such that we have equal number of elements, because the number of elements in a basis of a finite dimensional K vector space is exactly the dimension of this space, right? All right. Then we took an isomorphism which exists because the vector spaces are supposed to be isomorphic, so it exists by definition of isomorphic vector spaces. And then we took any basis BV of V, and we said, well, this basis has a finite number of elements, let this number be n, and let this number be called n actually, and then enumerate those vectors as v1 to vn. So we took a basis, and we know from the injectivity of L, we had this theorem, right? That L of v1, L of vn are linearly independent in W, because we had this theorem. If we take linearly independent vectors in the domain space, finitely many linearly independent vectors in the domain space, and we map them by injective linear map, then the images will be linearly independent, of course, in the image space. All right. Now we assume that it is no basis, because if it would be a basis, then we would have achieved what we wanted, two bases, one of V, one of W, with equal number of vectors in each, right? So now we assume it is no basis, and we'd like to prove that it is a basis, hence proving the claim. If it would be no basis, then the span of that would be not equal to W, because by definition of the basis, the vectors have to be linearly independent, and their span has to be equal to the whole space, right? And then if we assume that it is no basis, then the only thing now that could go wrong would be that the span is not equal to the space, because the linear independence was already established here, right? So if it goes wrong, then it goes wrong only here. That is, under this assumption, it would be true that the span of those vectors is not equal to this space, which means exactly that there exists a vector W in W such that those vectors are linearly independent. That we now claim that this actually implies this. How do we show that that span of these vectors is not equal to W actually implies the existence of W in W with the property that those vectors W, L, V1 to L, Vn are linearly independent. We show that via contraposition. That is, we show the following claim. We assume not all of lambda 1 to lambda n, lambda in K are equal to 0 in such a linear combination, which gives 0 under usage exactly of those L of the i's and of this W. That is, this is exactly what linear dependence of L of the i's and of W would say, right? So we assume they are linearly dependent. Well, then we have concluded that it is then impossible in this case, knowing the properties of the vectors involved, that lambda would be not equal that lambda would be equal to 0. So lambda is not equal to 0, and hence under these assumptions we can rewrite this like this, and we got linear combination that represents W. Right. And that means exactly that W is in the span of these vectors. Right. That is, we have gone from, if we assume that those vectors are linearly dependent, then the vector W is in this span. Using contraposition, if a vector is not in this span, then this vector together with first vectors are actually linearly independent. And that is what we do here. We have that span is not equal to W, and then there exists W element W with this vector not being in the span, which means via contraposition of this, that W, L of V1, L of Vn are indeed linearly independent. Then the R, then if these vectors are established to be linearly independent, then we can apply to them the inverse of our linear map to each of them, hence obtaining linearly independent vectors in V. We had this theorem that any linear map applied to some bunch of linearly independent vectors in the target space in reverse, applied in reverse, meaning we take any vectors in the corresponding preimages, that the vectors taken that way will be linearly independent, and this is what we do here. This is in preimage of this is in preimages of this, right? Of course, the map is invertible, so here the preimage is even the one element, so we can directly apply the inverse map, right? It's another way to see the linear independence. So anyway, we establish linear independence of L minus 1 of W, 2 V1, 2 Vn, 2 Vn. And this contradicts the assumed dimension V is equal n. That is, this contradicts that the dimension of V was called n by us, because this actually gives a number that is larger than the dimension that we assumed to be the dimension equal to the number of these bases. Right. Right. So we could see it even directly, because this wouldn't be by a basis spanned by this, but simultaneously it's assumed to be linearly independent. So there is a contradiction. And hence our assumption by which we started, that this is no basis, is wrong, and it is a basis, and hence we obtain the claim as I explained how we obtain it. All right. So we wrapped it up. And now that was a sorry attempt to do that. Just in few words, of course it's clear. Oh, okay, I shouldn't say that. But well, it is quite evident if you like get used to it a little within your mind, and you'll see that it is really evident. It's not that hard to see. All right. Well, actually, from the basic stuff, I think we only have one result left. If like I don't have a feeling like there would be another result that would be of crucial importance to know. So we have only one result left from the basics. And this is the following one. This is the theorem. Right. Let us also write like a remark before that, just so that you understand this. Of course, it kind of follows from the stuff we had, but nonetheless, let's call it remark. Remark. Since isomorphic spaces are same structure from the point of view of linear algebra, for any n-dimensional, where n is arbitrarily chosen, of course, n-dimensional vector space, that is for any vector space with a finite dimension, for any n-dimensional k vector space V, have that if we choose a basis BV is equal to V1 to Vn, the vector space V can be seen as or identified well, you can guess with what, which have just chosen a basis, so we have a coordinate map, so can be seen or identified with k to the power of n because of k to the power of n being simply isomorphic by coordinate map BV. We could take the inverse. Doesn't matter. Well, okay, let's take the inverse, but okay, it goes in both directions. You could just take this, right? The inverse it is invertible map, but you could also read it like this. So isomorphic 5 is mapped without -1. We have shown that it is an isomorphism, right? So yeah, it's also an isomorphism. Yeah, right. Because of this, so we can naturally identify any finite dimensional vector space with just the vector space of basically its coordinates, right? But don't forget this identification is pinned on this basis, right? It's important. Another basis would give, of course, another identification, but basically, yeah. They behave kind of the same, right? Well, oh, okay. I remembered an important topic. An important topic. Right. Let's play with representation matrices of linear maps. That oh, Right, and I remembered also lemma. I want you to show things long, but it is pretty simple, so I omitted it the whole time, but yeah, it is kind of useful. Lemma composition of linear maps. Oh, you could guess, is itself linear, of course. Maps is itself linear. It can spare a lot of time by considerations or also by some arguments, right? Okay, proof, very easy, just straightforward, check definition. Proof, well, that equivalent easier thing for this easier thing that was equivalent to the definition. Well, you'll see in a second. Let L W be a linear map. Let's call that a WX be a linear map as well. Then have to check for V1, V2, element V, lambda, element K, have, can do a composition, right? Have to check that A, L, this is the evaluation of the composition, right? You should know that, how the composition works. We have to check that this map A composed to L, right, is linear, which means exactly that's what I'm writing down right now. Right. Have to check that. Well, and that's pretty straightforward. Have a we actually have done similar stuff by coordinates when we considered coordinate maps to establish a matrix. To establish the correspondence of applying matrix to a coordinate vector through applying the linear map to the abstract vector, right? We actually did that on foot. Should have stated it back then we wouldn't have had to do this. But, well, let's just state it generally. So I'm applying linearity of L and then I'm applying linearity of A, right, with the elements of V1, of V2. And this is already proved. Right, that was easy, right? All right, and with that, with that we want to consider the some games with representation matrices. Actually, it's simple, but let's spit it out. So, all right, let's call it I don't even know what to call it. Some considerations. Let what will we need? Well, for now, let's just L, V, W be a linear map dimension k v, that is v is a k vector space. That's a shortcut to write dimension, and we field of a vector space cons dimension k w is equal to m. All right, let b v equal v1 to vn, vw equal w1 wm, the basis respectively of in w, of course, respectively of v and w. Right. Well, what do we have next? Right. Then consider first the identity map. Well, there's something that I don't quite like, but okay. Consider the identity map. Okay, consider the identity maps. W, where of course now the identity map, well, what could it do? It just maps an element of V to this element itself, and W does same thing. Right. Then we now consider different representations of the identity map. And yeah, you might ask yourself, what the heck? Why? Well, you'll see. So we consider it now represented with respect to basis BV, and we map into the space, and we have again representation in coordinates of the same basis, right? What would that be? Well, you remember that you just have to take coordinates map of this in that very basis. Because we go to this basis, we have to take because we start with this basis, we have to have here the coordinates of the basis BV, right? Because we go to this basis, we have to have the coordinates of the images of our map to represent in basis BV, right? That is why that looks like that. So don't be confused because we have chosen somehow same thing. Doesn't matter. You just consider it separately. You have to take vectors v1 to vn because we start at this basis, right? Just by the description, which we had before, I think, 2 lectures ago or something. Of course, this is the last vector in the basis, right? I go through all of them. And you have to consider here same basis because you actually have this basis as the target basis, and so you have to map to the coordinates of this target basis to get the representation of this map. Well, you recall that this is V1 and this is Vn. This is boring. This is just the how the identity map works, and this is just, well, remember that this is just element of, well, n coordinates in n bases, and recall that this was one of zeros, so this is the vector e1, namely in k n. By the way, maybe worth mentioning, this is of course 1, not in r doesn't have to do anything with that. This is this vector in k, right? And that is, of course, this vector is, well, I mean, equal 0, 0, 1, which is n, again, n, of course, in kn, and we have n, we just have ones on the diagonal of this matrix, which means that this matrix is exactly the matrix In, that is the matrix, don't mix it up with the notation for the identity map here, which is with space. Here there's just n4 instead of kn, but this is of course same as in on kn, because on kn the matrices and the maps are identified directly. Oh, clearly, because you can just consider the standard basis and you can identify them directly, right? But well, you have to think about it a little maybe, but here, right? And this is n cross n identity matrix, so nothing interesting. Same way, IW, PW, PW as representation. Okay, I should write where it is. And this is IM, and this of course with ones in the space k and diagonal k and m. Right. Well, now it occurs to me that we need an additional lemma. That's namely the lemma that this composition of linear maps, right, will be represented as composition of matrices in coordinate fashion. Of course, it is very self-suggestive and it is like that, but let's prove it. Right, lemma let L from P to W, A from W to X be both linear well, let dimension V and dimension W equal M dimension X equal K. So in particular, the dimensions are finite. Let PV, PW, PX be respective bases. Then have, well, what we have is that the composition of maps has the representation composition of matrices. that is, well, we go from V.V., right? Sorry, I mean, of course, A composed with L. So first we carry out L, and we carry out A, right? PV to Px, of course, is simply equal, well, what would you guess? It is equal to matrix multiplication. A, and exactly same order. First comes A, B, O, where is A, BW, BX, right? And this is just matrix multiplication, right? This is just matrices, as you recall. PV, PW, right? All right. This is, of course, maybe it requires a little bit of time to get used to it, but as you know, it is not quite difficult. Right, okay, where are we? I always confuse those things. Well, we want to have the row vector like this, and we want to go from n, right? This is kmn. This should be, well, we want to go from w, and that is we have m columns now, because this is multiplied like row wise with vectors multiplied, and this is bx, and this is k. Right, and this, of course, is, well, you could look at map in matrix multiplication, so it would be k cross n. And now check that. Well, PV, we go from V, and we take the spaces, so the vector is has n columns. We multiply with this vector, the matrix, so the vector has to lie on the row properly, right? And we have how many lines? Well, we want to have k coordinates, right? Want to arrive at k coordinates, and well, you see the dimensions fit, right? And now we have to prove it, right? Proof. Well, the proof just works via the coordinate maps. You see, well, let the element v then, well, you recall what were the what were the matrices, the corresponding matrices, right? Then, a bw bx is equal to, well, just take a basis. Okay. Of course, we should take a basis, but well, let's call the elements just in a suggestive way, then we can avoid it. Okay, that is bx, right? Because we arrive in bx and we go from w, right? So we take and we go from the basis bw, so we have to take a of, so the coordinates of a of, well, of what? Well, let's call it bx1, right? And that is up to phi bx, have to take those coordinates because we land in x, of course. So have that, and how many do we have in those? Sorry. I told you we go from w, so we have to go from 1 to m. You see, I get confused myself. We go from w, and we have bw here, right? Because we have to go through the spaces bw, and we have to map those spaces vectors in the domain space, which is W here because we go from W to X, right? And we have to map them, and we have to look at the coordinates of them in the target space, and this gives the representation matrix for we map A from W to X, right? And we have how many vectors in total? We have M vectors. All right. All right, this is one matrix, and this is L, and L goes just from PV to BW. That is same game. We have here everywhere we go into BW, so we have to consider coordinates in there, and here we have mapping by L, and we have if we have started in BV, right? We have started in BV, and we go from 1 to N. Right. And then we obtain, of course, this matrix here. Right, BV to N. Alrighty. Well, now we'd like to multiply that, and we'd like to have the composition as result. And the composition, well, how does that work? I mean, we'd like to have the matrix representation of composition. And we have what do we have here? Well, we have, of course, we go to X immediately here, and we go from BV. Right, and the map that we have to apply will be a composition L, and the corresponding vectors will be Alright, what will be the corresponding vectors? Let's see. Well, we go from BV, so that would be just B1, B2, B, and B, right? This is evaluated that evaluates that evaluated at that, right? And this gives you 5bx, A, B, and V, right? And this gives you that. Right, now how do we do that? How do we show that? This is exactly the same. Well, for that, of course, we would have to use some things. Right, let's think about it. We would multiply. And here we would have the coordinates, all right? And if we apply that to that, all right. All right. Okay, that should be fairly easy. That's just technical proof. You don't have to think, actually. That's what I would think. We could have, of course, now written down that and have seen what comes out of this, but it's no fun, right? So I want to see that like immediately. Best would be to see that immediately. All right. Okay. 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 Of course, we could do that. But no, it wouldn't work like that. Okay. Okay. Well. Ah, yes, yes. Okay, I see, I see. So, you see, the thing is, when we multiply that by that, then this, we go through the line here, right? And we multiply it by the column. And the column contains exactly the column contains exactly the coordinates of those images under L, right? So it's kind of like we put a first component of mapping with respect to A on those coordinates here, right? So it kind of makes sense, right? And what happens then? Well, the thing is, all right. Well, I'm not sure if I can see through this. Well, well. And this is supposed to be the first coordinate of this, right? So it is kind of like we should have those things integrated into this. All right, all right. Well, the whole thing is the whole column is taken up by this, and that way we obtain like those coordinates being multiplied by those, right? And then this should give those coordinates, right? So this should give those coordinates, but how do you obtain those coordinates? Well, that is worth um, um, this is worth consideration. How do you obtain those coordinates? Well, you have to map. You have to map this by this, and you have to map this by this. Right. And Um, by doing so, well, yeah, is a part missing? Wait. Well. Let's do the following. Let's do the following. Um, yeah, I think I would do it like that. Okay, let's do the following. Have bx a. Now carefully think about what that is supposed to be. Well, a is a map from w to x. So if it is a map from w to x, and this is of course supposed to be w, and this is supposed to be of course be w minus 1. This is by the way a common trick. I don't know if it will work, but I hope so. I hope that it will lead us to some ideas. But yeah, I'm almost seeing what will happen. Alright, when we have that, like you see, this is identity, so I haven't changed anything. This is just identity map, just identity of W. Right, and then we have L, and we can again do the following. Well, where do we start? We start at PV, and that is we have that, and then we have. So what I did was not change anything, but introduce forcibly, I introduced PV and PW into here. I introduced PV and PW into this here. I mean, I introduced, of course, the coordinate map of PV and PW, but well, that is kind of introducing the influence of PV into that of PW. Right. And you see here, oh, what do we have here? We would like to show that this gives those coordinates, right? If we have that, and we would have just our okay, let's not call it, let's just take a arbitrary column, of course, V.IV, right? This, under this, would just be our unit vector. You recall is the combination of map is associative, so we can also do that. And we can do that, right? So, and we can do that. Right, we can do that, of course. And well, this is just, well, this is I, and this is in EI, right? 0, I, 0, 0, and this is ith position. Ith position. Right, and what do we have here? That's a good question. What's that? Well, you see, that is just Well, if we put that, right, we just took this and we put that, and this, this is a map that just goes from, this is inverse, right? So this is a map from Kn to Km. Okay, I should not write it in totally different way than usual. Of course, it is a little bit confusing how it is here written, but we have to keep that right. Right. So this does what? This actually maps such a vector, right? It maps this vector just by definition to the coordinates V.W of what? Well, of this vector V.IV. Right? We're just considering what is happening here. We took this vector, we got its representation in this space, and then this map just took this representation from this space, right? This was the representation of this, so it took it back to V.IV, right? Then it mapped that by L, of course, L of V.IV. Then it mapped that by L. It's just considering what the maps are doing, right? And then it took its coordinates. So we get exactly those coordinates. And this is already a good news because, well, we kind of are here now, right? This is already good. But now we should understand why we have this weird multiplication. Right. So I should write it properly. By the way, yes, I needed that because I need to introduce that, right? That is right. And then I get that. Right. So, W of L of indeed V.IV. Right. And then we have just to look what happens here. But actually, we don't look what happens here. We could also look what happens here. Well, yes. Because the composition is associative, we just have that, right? We have introduced that, and we have introduced that, which are just identities, so nothing changed, and then we used associativity. Right. Well, and of course, what we had that was that was equal to px of a of L of V I V. Right, we have just introduced those maps, which we can do. All right, and then we have that map, and this map just takes that vector, maps it by A. And what does mapping by A mean? Well, mapping by A to obtain those coordinates means exactly multiplication by the matrix A W Px, right? Because we take this, we take the coordinates, right? We just took our coordinates. This takes the coordinates, this applies A, and this gives the coordinates back. So this is nothing else but the matrix itself. And you can guess that this is also nothing else but the matrix itself. It is just what this map does, right? It goes from the right space, from Kn now, from this universe map, so the map itself went from V to Kn. This map goes in from Kn to V, from Kn to V, from V to W, from W to Kn, so V dimensions, right? And the map is doing, which are just looking what the map is doing, and it is doing literally what this map does. It's just that it is mapping every vector in Kn to exactly the coordinates of the to the W coordinates of L of the image of this map, because we take the coordinates, we go to the image, we apply the map. We take the coordinates in V or in V of the vector V, and we apply to these coordinates our map that brings that back into the vector space V, so that we obtain vector V back, then we apply L to V, right? And we take its coordinates. So this is exactly this. Right, and of course, if you want to have it rigorously, then you would have just to write down that shows what? That shows that, well, let's write it down rigorously. That was just our considerations, what we think somehow works or whatever. Let's write down rigorously what actually happened. Well, I have a B, V, B, X, and well, I'm just writing it, of course, column-wise. You could just apply it to every column. Nothing would change, right? The if column would be phi bx a l of biv, right? I'm just taking the if column, and you could apply that in each column all the same, because, well, what we have is actually phi bx a, this is composition, L is applied to the vector biv, and, well, if we insert identities, nothing changes. Phi bx multiplied by a multiplied, multiplied, I'm calling it multiplied, even though it is application of a map, but you see why. Right, now you should see that why. I mean, by now in our course you should be able to see why. All right, phi bv minus 1 phi bv, and this is applied to V.I. So contemplate why this map is exactly the same as this map. I have told you why, but think about why inserting identities actually doesn't do anything. If you have trouble with that, ideally take an element and think about what happens in between here. Just take this map A, composition L, and take this map and just follow through for each element, or for arbitrary element, I mean, of course, what happens here, and you see that it works indeed. Right, so applied to the same vector, and this is, of course, well, associativity of the composition of maps gives you a phi bw minus 1 phi V.W 5 minus 1 V.V, and this is applied to the vector V.V, V.I. Right, and we have established that this, and this is just clear. This is just that this map does exactly the same as this map, goes exactly from the same space to same space. So of course it's the same map just by definition of equality maps. But you could of course follow it through very rigorously what happens here. You see what happens here. I took an approach from viewing it from the bird flight. Of course, it's mathematically completely rigorous, but if you can't understand it right away, then you should really just think what exactly happens here, or what exactly happens here, what exactly happens here. It's actually just here, right? I mean, just in the sense how I explained it. This applied to this gives exactly that. But this giving exactly that, wow, you should write down the vector. If you don't see that, you should write down the vector and its coordinates. Look what happens to the coordinates, and look what this does to where to it maps the vector, and look at what A does with this vector, and look at what phi bx does with the image, and then you'll see that it works. Right. V.V, V.W, and this is our coordinate vector V.IV. Right. Wow, and what do we see? We see that this column arises as matrix multiplication of this matrix with this column, which is the if column of what matrix? Well, of the matrix. Oh, of the matrix. Well, you recall that this is the if column EI of the matrix IN, because this is just basis coordinate map in the basis applied to the if basis element. And this, of course, gives the if column of the multiplication of the both matrices. So this is equal to the if column of the matrix multiplication like that, right? Okay, I would understand if you have trouble with this, because, well, back then I had trouble with it myself. Because it's just it's too many things at once, and everything should be actually realized clearly if you want to have a solid foundation. Of course, there are a lot of people who just accept things and think that they have understood, but well, of course, some of them are also right, but some of them are just not diligent enough. And if you need to understand each step, then really take some time and understand the steps separately without worrying that you have to understand them all at once. There are so many steps. No, just concentrate on a single step, think about establishing it. Also, you can doubt if I'm right or wrong, so spend time understanding some step, you understood that, then you can put it into the whole picture in the next step and things like that. Of course, might be, or at least in your opinion, might be that I'm wrong. I'm pretty sure that I'm not wrong in the steps I'm doing. So, but it's like I always questioned the steps, right? And many times I was wrong. Very few times I was right. So and yeah, you have just to spend time contemplating it properly and really diligently dealing with every little thing that you have trouble to understand. This is just how it goes. If you want to learn to deal with things properly and to your satisfaction, total satisfaction. So now we have the if column of this matrix is equal to if column of this matrix. Matrices have same dimension. These matrices have same dimension by matrix multiplication. And this is what we wanted. We have established the equality of these matrices. Also, corollary of the way how we prove that. How we prove that, right? Corollary of the way, and then we have this nice thing. All right, so composition of linear maps. When bases are given in all spaces of interest on which they are defined, obtains its representation matrix exactly as the multiplication of the corresponding representation matrices. Right? This is nice. So composition kind of carries over to matrix multiplication. And this is also what really happens in truth, how we can see that from an upper level composition of linear maps is a linear map onto the matrix multiplication. A linear map that identifies, the map that identifies linear maps with their representations with respect to bases. This linear map, this map is indeed linear, and indeed the operations are composition and matrix multiplication. But well, that's what we want to establish. After we have dealt with representation matrices, all right. Corollary of the way we proved, of the way how we proved above theorem. So following, let L W linear dimension V is equal to N dimension W is equal to M. Let BV equal V1 to Vn, BW equal W1 Wn, be some respective basis. Then the matrix representation of L with respect to the basis B, V, W is equal to, well, this map that maps from what? Well, this is a linear map, recall space of linear maps, right? This is a linear map. Right, this matrix defines linear map, and we can just identify the linear map defined by it with the matrix, right? And this is linear map. Actually, I have already done it here. Right? Because well, I have done it in a way because well, kind of assumed that this is exactly the matrix, even though it was linear map defined by the matrix. But the important thing is, if I know that this map actually gives applied to this vector exactly the image of this matrix, then I can of course replace that by this matrix applied to this coordinate vector, right? Because if the result is same, then I can replace by the result, right? So it didn't matter. And here, um, same, right? So this is the representation matrix, this is linear map, but this result applied to this gives exactly this map applied to this. As I said, you should contemplate that it is indeed the case, and then I can replace by the result represented now in terms of matrix applied to this vector. Right. Okay, then this is by terms of identification with this linear map. And if you are wondering, of course, I mean that V.W defines linear map via lambda 1, lambda n, right? This is the image. I mean, this matrix now also we call same linear map. This defines linear map via and linear map from here to here via mapping. This was our very first example of linear maps, right? Or one of the first examples via this. So right, so this is identified with linear map, and this linear map is indeed just the map phi pw l phi pv minus 1. Yeah, again, just look. This is what we have discussed here. Just look at what it does to a vector and just establish that the result is the same as by this map, right? For that you have written down really v is equal to the sum, blah, 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 blah. And you can look at what this does or what this takes from this v and so on, and then you would establish it. Right. This is good. Now we have connected representation matrices with composition with coordinates maps, right? So this is very good. Okay, have to take a minute. Oh, by the way, let me tell you, this kind of theorems are not theorems that you should learn by heart. Of course, can to apply them quickly, but of course only with the complete understanding of what you are learning there. And it's better to see how the structures are connected. Because to apply it intuitively right and in unfamiliar settings, really have to get the heart. You have to get to the heart of the matter. It would not suffice to just learn it by heart somehow. And there's also, if you separate that in little theorems, there's a lot to learn. I'm also not doing that here because it's not the point. The point is just to enjoy this interplay, right? It's not some crazy theorems where the assumptions that where they get in really comes in only after some few steps, and it is not obvious that those assumptions are needed. No, it's completely structurally obvious theorems after you have contemplated it a little. Of course, there's some technical thinking through it. Of course, it has to be like it. It's mathematics. I mean, that's basics of mathematics. Of course, there are a lot of technical steps that you have all to follow through in your mind. I mean, also by recalling them and by thinking about the connections between structures, but that's really what you have to do. And I mean, there are no special tricks in it. No, um, no surprises, no sudden realizations. I mean, after you have internalized that, of course. So this is not the kind of theorem you should learn by heart, or not the kind of theorems. You should really understand what is going on. You should be able to carry those manipulations out yourself. Well, in the best case. Right. So do not just learn it by heart. All right. What do we do next? And we considered representation matrices, right? Now we have established some connections between representation matrices and coordinate maps. All right. Well, what we do next? Right. Let's continue our considerations. We have that those are just some matrices, all right? And now let BV be the children be both bases of V. Then what could we say about the matrix I, meaning identity of V, BV, BV tilde. That is, we are just mapping by identity map, and we are just taking this matrix and, well, just the vectors we want to have. We want to map vectors to same vectors, but we want to have the coordinate output in with respect to the other bases, right? We can do that because identity is a legitimate map, and we can just take those bases to represent this, and this is the meaning of what we would get, because when we take such a representation matrix, this is what we are getting. Taking coordinates with respect to this basis, we apply the map to the vector, to the abstract vector, get here same vector, and we take coordinates with the other basis, respect to the other basis. Well, what could we say about this matrix? Of course, we can also play the game our way around, where we switch the bases. We start with these bases and get that F IV BV BV children. This is matrix multiplication. IV. I could write a dot, but I'm not doing it. Doesn't matter. We know what is meant. BV. And well, from our composition theorem, we have that this is just the representation IV, which is IV itself, of course. What else? Just map vector to vector, and map again vector to vector. So this is just VV, VV, IV, which is the identity matrix IN. Recall that the dimension was, well, actually it doesn't matter, but we called it N here. Dimension of V is N here. Right. All right, and same way we have IV B now from that side VV tilde VV IV B V VV tilde is equal I. That means basis switching matrix. This is a basis switching matrix. Basis switching matrices are invertible. Matrices are trivially invertible. Matrices are trivially invertible. That's nice, right? Now, well, you can guess what the generalization is. Take an invertible, because identity here was invertible, right? Take an invertible linear map. And we know invertible means bijective, so it is an isomorphism, so the dimensions of the spaces should be equal, right? So we could take V.W with dimension V, and I'm just specifying, I'm just giving the number a name. The dimensions are equal, but I call them N. So I'm calling them N and not M or something, right? Then call equality is from invertibility, right? Because that means that L is isomorphic. And call the dimensions N and have, well, bases are called, as always, BV, BW, right? Or some bases that we choose are called BV, BW. Well, and you can guess that, of course, same way we just get identity, right? L minus 1 BV. Okay, I should pay attention to where we go from. We go from PW and we go from that, so this taken this, and this taken this second one, right? Alright, PW. Which is, of course, again, the identity matrix, and so IN. And so we have that, okay, remember that to show invertibility, we have to show both directions. Does not necessarily follow from this one. Okay, in case of matrices, it does because of the determinant, so we don't have to do it. Okay, in case of matrices, it does, right? Because, well, we just take the determinant of that, and this is right. In case of matrices, it does, no problem, right? So what we have that the inverse of a matrix is exactly the representation matrix of the inverse map, right? So in particular, the representation matrix of an invertible map is invertible, and invertible with what? Well, of course, with what else could it be invertible? Of course, with the representation matrix of the inverse map. Of course, with respect to same basis. So if we would switch bases, of course, we would have different considerations here. All right. So, conclusion. Any representation, any matrix representation, of course, but it's clear from the context. Any representation of an invertible map is invertible is an invertible map is an invertible matrix with the inverse being that being representation of the inverse map with respect to same basis. But of course, we have to pay attention from what space we go and which basis is now here and which here. Same basis. Right. And this is our considerations. What else would we like to have? We had that decomposition, kind of composition of matrices. All right, I think that's it. All right, let's take a look at something maybe. Given a linear map, L V W dimension V equal N dimension W equal N have now what do we have? Oh, we could start in W, right? We could take our map PV and basis, BW and basis. And we can go to W, right? That is, we just take an element and go to W, right? But we could also do the following. We could go via k to the power of n via the coordinate map, right? Phi PV, and then we could go by our matrix to the space Km and that is our matrix representation L, PV, PW, and then we could go via inverse of the coordinate map PW minus 1 back to there. And this is called the commutative diagram because the diagram commutes, see, this way is same as this way, and this kind of is a shortcut for composition, right? Compose this, compose with that, compose with that, gives that. But of course, you have to keep attention. This is now left to this, but actually that would be put here because we start here, and that would be put here, right? So yeah, this works like that. And of course, if L would be invertible, we would have that another way around with inverse matrix, and with this inverses everywhere, the arrows would be reversed. Right. Furthermore, let A be from W to X, dimension X equal K, again finite, Bx and basis, and well, what do we have then? Well, then we could go from V to W to X here via L, here via A, and we could go from V to K, N. Here we could go to what K, M, via, of course, representation matrix L, with respect to a basis PV, PW, W, here we could go to K, K, with matrix A, PW, Bx, here, of course, this is coordinate map, right? What else? I, VV, I, Bx, minus 1, of course, the other direction. Here, of course, we could also go like that if you like. So you see, you can play around with this if you like, whatever way you see fit. 5 minus 1, B, and W, and well, yeah, things like that. You can just compose them in whatever way you like if you just pay attention to how it works, right? So what else? Well, that, 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 and you could also go, of course, from here to here via your and you see already I'm identifying linear maps defined by matrices with matrices just like that because it's very obvious here that the results will be like that, right? And this is just PV, PW. Of course, pay attention that you get the order right, just like I got it wrong now. Okay, Bx, which is actually equal to composition L B B Bx, right? As we have established. Oh, so you can play around. Those things are called commutative diagrams because you could go any way, and this gives you the map how you could go. And this is not geometrically because this would be right something. It is in sense of what is applied first, what is applied second, and how we can go to where we want to be. You could, for example, when you are faced with a task to compute some coordinates or something, I don't know, you could write for yourself that scheme. You could just think, oh, obvious is this, and where could I go from here in an obvious way? Well, of course, by coordinate maps. Of course, here also here by coordinate. And then, well, how could I go from coordinates to coordinates in the basis? Well, by matrix and so on. And well, you can think about such stuff if you like. Okay. I think we really have only one theorem to go to cover the basics, to finish covering the basics. Yeah, I really think that. Alright. I don't know if we can prove it quickly. Let me at least state it. Theorem. Identification theorem. Of linear maps with matrices given finite-dimensional k-vector spaces This is, by the way, kind of main theorem of basics of linear maps. Oh, dimension formula in this. Theorem given finite-dimensional k-vector space. And in case you are wondering, until now we have identified the evaluations. Now we are really identifying the objects. And we are identifying them in a very proper, rigorous way. Even finite-dimensional k-vector spaces. V.W PV 1 to Vn PW W1 to Wn some basis some basis have an isomorphism and recall the spaces that we will consider now in isomorphism. Now, W psi. Recall that this was the space of L V to W. L is linear. To what space? Well, what would you guess? K and wait, and no, since we want to have matrices Km cross n over the field, and well, what is in that vector space? We addition, well, just a normal addition, and here just a normal scalar multiplication. So nothing interesting, right? And how you do that? Well, very simply. Just proof just define proper basis of a set of a space V.W and map it via linear extension. You recall we first defined the images of the vectors and then we extend linearly, but we will do that, so no worries. Linear extension. Proper basis of a space of V.W and map via linear extension so that images of basis vectors are respective standard basis vectors, that is matrices with one entry 1 over entries of 0, and of course any entry would be one time in whole of the basis, right? So basically an analog of the unit vectors E1 to En matrices, right? First the entry 1 of the matrix is 1 over entries of zeros. Then the entry 1 2 of the matrix is 1 over entries of zeros. So various vectors like this are respective standard basis vectors of K M cross N. All right. Well, why would this already give an isomorphism? Well, because the dimensions would be equal. Okay, we would have to define something, and the dimensions would be equal. All right. Dimensions would be equal, of course, because we would have to map different. All right. Dimensions would be equal, and furthermore, the map would be surjective. Well, of course, if we have mapped to all standard basis vectors, then we just have to take a linear combination uh, in our original space, and then just having that limit as linear defined by a linear extension. So it is linear. We just apply this and get as images of the basis vectors the standard basis vectors, that is, the constants in the image get multiplied by the standard basis vectors, and this of course gives any matrix. And furthermore, the map is automatically surjective. Automatically surjective. If you don't see it, just take any matrix and take corresponding linear combination in our vectors of the basis that we will construct and then map by our map, and you will see that. Right. And corresponding combination means just same constants by same corresponding vectors, right, in the domain. And furthermore, the map is automatically surjective. Right. Well, how do we define a proper basis? Well, we just let us inspire define a proper basis. Define a proper basis. Proper basis of W. Well, inspiration is just matrices, just the basis of matrices. Inspiration. Matrices. Entry ij. And everything else is just zero. The only one entry is not zero, right? And we just go through all entries, right? And how do we define that basis? Well, accordingly, define Fij. This is now supposed to be a linear map. We don't know yet if it is linear, but we'll see. Fij from V to W via. And we had this thing that it suffices to specify the images of basis vectors in any way, so we just define that Fij via Chronicle delta ij of well no, sorry, yeah, in a way, but yeah, okay, I see. Vi Chronicle delta. Wait, sorry, we can't Ah, yes, all right. Chronicle delta, of course, now takes values in the field, right? So chronicle delta from vector space ij, but it's just a fancy way to say something very primitive. W j, right? So we take the vector vi to this chronicle delta, multiply by that, where chronicle delta goes from our vector space v to our space k, and it does the following wij. Mm, well, that's not what I wanted. That's not what I wanted. It's totally not it. Hmm. Oh, wow. That's annoying. What I wanted was to define Fij as mapping. Okay, as a mapping. Of course, what else could it be? All right. Okay. It goes from L or from V to W, and it does the following: fixed I j, right? So it maps vector vi to wj, and it maps our vectors to vi tilde is mapped to 0, which defines linear maps, we know, because we can specify our basis vectors in any way that will define a linear map, right? And this is for I tilde not equal to I. So any I tilde not equal to I, any Vi tilde with I tilde not equal to I is mapped to 0. All right, and this, of course, we keep I fixed now, and we go through all j's, which will give us a map that now maps Vi to this Wj, right? Now I is kept fixed, so next map will map next Vi to Wj. No, next map will map same Vi to, oh, we started, for example, by W1. Vi was mapped to W1, everything else was 0. Now we map Vi to W2, everything else is mapped to 0, I mean in the basis. Then we map Vi to W3, everything else in the basis is mapped to 0, and so on. And indeed, this defines a linear map. We had this theorem that specifying the images of the basis already defines a linear map. That is, there exists a linear map that does this. Now show that mapping. No, we don't need to. Well, what we only need to show. Okay, we need to show that it is linear. Right. If we have shown that it is linear, then we already have same dimension, because the dimension of a metric space is obviously k multiplied by m. Okay, we have to show linear independence. All right, now I get it. Okay, well, Fij Okay, there exists a linear map, so it is linear. Don't have to show Fij linear, so that works. Define Fij linear via this. We know there exists such a linear map, so we can define it like that. And we know linear map is already determined by the images of its selfie basis vector of a taken basis, so it is also determined, right? And well, what would we like to do with that? Well, now show that we are linearly independent indeed. Now show, because we don't know yet if it is a basis, and that it is that it spans the whole space, pretty obvious, but show that too. Now show the maps are linearly, but it's really also pretty obvious, linearly independent. Let lambda ij be in K such that we double sum ij lambda ij Fij is equal to 0. Well, and we recall that the zero map was a map that mapped everything to 0. That is, this means exactly that every vector must be mapped to 0 by this map, and recall that the operations that we maps, scalar multiplication and the plus, work just pointwise, and for other than that, just operations in our vector space. Then we have for V.I element V, that is, we go through all element BV, we go through all the i's and the bases, right? We have that is actually 0, lambda ij, Vij Vi is 0. But what's that? Well, everything is 0, and other than that, we have lambda ij. Okay, sorry. We have then that this Vi is not 0 only for those maps that map this Vi to some Wj, and for all others, it is 0 because we fixed one of them and we mapped that to some Wj, but for other map, it was fixed another vector in here, and all other, including this one, at which we just were, was mapped to 0. So this is just the map, the sum over all j's, lambda ij is f ij, and you see I suffixed, of course, because we want those for which this is not 0, and from linear independence of the vectors, this is just Wj, right? You recall, this is just how it was defined, right? We conclude from linear independence of Wj's that this is 0. because recall that WJs were elements in the basis of PW, in the basis PW, right? By linear independence of PW, that is all elements in PW, and that we can do for every I, and with that we have gone through all lambda ij's, and this gives then what we wished, hence the vectors are linearly independent. So ij's are linearly independent. All right. Now, obviously, we spin the space, but let's look at it. So spin Fij is just the set that goes through all Fij is equal to the space of linear maps here, and we know it suffices to get we know that the linear map is already determined by its images, so I just look at the map A element of W as determined by images of the vectors in here, of course, that's what I mean. Obtaining well, what do we obtain? A of Vi is equal some lambda ij's just by this is some vector in W, right? We just have that this map maps it to something, and this image is determined this map, as we know, because this image is a basis vector, but this vector to which it maps it can be represented with respect to the basis W, which we already do, and we get some constants which are dependent on I, because here we have considered this image, and we go through all J's because we have to have linear combination of all basis vectors in BW. Right, and this is for I. It is for I in 1 to n, obviously. Right. Just look at this map. Is determined by images, blah blah blah. Then set. And this is so you can probably guess. Then set. No, then get. Then get. A is equal lambda g Fig. And please don't mix it up with this here. This was one part, and you should understand that this is another context. This is of course not same lambdas here. They were just any lambdas, right? And we have just take some for the sake of argument. Here the argument was finished, so this is just some lambda ij's, and we are interested in that they exist, right? And this is because for Vi element V have ij lambda ij f ij wi I mean vi is equal what? Oh, this is equal obviously, well, everything but vi's disappear and all vi's stay, and with what do we stay? Why? Of course with that. Sorry, I'm too fast. vi. This is just j lambda ij wj, right, by definition. And look here, have that this is exactly a of vi, and since the images determine the linear map uniquely, this already shows what we wanted. Right, so this spans it, and this is a basis, so indeed, this is, I mean, this spans it, and this was linear independent, so indeed, Fij is a basis of what of L V W. Right, that's great because the number of elements in this basis, just how we have defined it, you can check yourself. It's very easy. Is n multiplied by m because I went through all n through 1 to n, j went through I to m, and so the number of vectors in here is exactly n multiplied by m, defined in, and we know that this defines linear map, right? Because it suffices to specify the images. We actually don't even need to make linear extension specific because we know it suffices to specify the images. It maps to eij, and by that we mean that we define this psi isomorphism L V.W to the space K and M. Of course, it also has dimension M multiplied by N because we just have that many possible positions for once, right? So that many vectors. Right, and well, I have to show that it is an isomorphism, but since Fij, okay, we can't do it like that, sorry. We can't do it like that, but we can do a different thing. We know there is such linear map, right? It's just we specified the images of the basis vectors, right? Linear, since psi is linear, okay, we can't do that either. Okay, I get it. But well, it's really easy to show that don't have to do linear extension, but shows surjectivity now. VMAP exists, right? We show psi surjective, right? Psi surjective. And the dimension formula, right? Surjective means that the image is equal to space. Now the dimensions are equal as we established. So we get the injectivity, and with that we bijectivity. In the dimension formula, gives then psi bijective because of by the way, that it is a basis of K and M. That should be clear, but you can look at that yourself. In psi bijective, psi is gives them psi bijective, right? Because of dimension L V W is equal M by N equal dimension K M cross. Right. Oh, and this is really easy. Let well, that Aij, just a matrix, right? Aij, with the entry ij being Aij, the element of K and cross M, and psi of exactly that thing. Psi is linear. Fij, ij gives you exactly Aij via linearity. That is mapped. Psi, I use linearity. Psi of Fij is exactly Eij. So you have Eij here. And that is just trivially Aij. Ij. As we liked to have, right? And this shows that it is an isomorphism. We have shown, first we have constructed it linearly, then we have shown that it is surjective, and we established also that the dimensions are equal, and surjectivity gives already bijectivity, and with that we have finished it. And well, corollary. Corollary. Dimensions. Dimension of W in situation as no, we can do it simply in that way. So we can really identify, since the space is isomorphic, we can really identify the matrices with the linear maps, right? That is great. So what we do really makes sense what we did about that. right? Dimension of V multiplied by dimension of W, which were M and N there, N and M respectively there. So, right, if V.W finite dimensional. Let me maybe define something that we might want to use. Definition. Call rank of L. Rank of L B B B W. Of course for L B W linear B W finite dimensional vector spaces. B W some respective basis, so it doesn't matter which you choose. That is why, well, just suppose we would have another basis like L B V children BW children. Oh, what would that be? Recall this thing with composition of matrices being exactly composition of maps. Call this, let this be just identity on the space W, let this be identity of space V. Right, V children. Okay. I mean, here, V children, P W children. This is, and as you recall, this can be represented with respect to something, and we have just to find bases that are proper. Well, the basis that we'd like to have is, of course, you can just check it with our theorems above about identification of matrices. That's just based on that. Right. W children here want to be. That is L with respect to BV, BW. Alright, and that is finally. So you see, you can play around with these notions. And this is, of course, great. And this is PV children, PW, PV children, PV. So we go first to P2 B. We go first from representation of a vector in V tilde V to BV, then we go from BV to W, so apply our map in matrix form, then we go from W to BW tilde, so we get exactly this thing. We apply the map and we switch the coordinates, and these matrices are invertible. As you recall, basis matrices are invertible. Invertible. Hence, the rank is well defined because we think of any representation matrix would be exactly the same, so we could just pick any representation matrix and we can define the rank of the linear map that way. Right. I hope you got the argument. If not, think about it a little and that you realize what things I have used here. This is just the identification of the matrix multiplication with composition of maps representation, right? And well, this is of course right. And well, that just gives you that the rank of two matrix representation, the rank of matrices is just the same, and that allows us to define that, right? All right, I really think that finishes the basics completely. We have covered everything that we'd like to cover. Well, maybe I'll have another ideas, we'll see. But, well, I think, yeah, the basics are finished. I hope you enjoyed it, and, well, I'll see what I'll do next. Maybe we'll go further into interesting stuff like basis with scalar product, maybe Jordan form, or yeah, things like that. Special types of maps, or maybe I'll do more elementary stuff. I don't know. Maybe calculus. Well, we'll see about that. I don't know it yet, but yeah. The basics of linear maps we actually covered, I think. That's all you have to know. Yeah, alright. I stop here.